All right. So, as I said, so far we've got 3 of our 5 connectives. The only ones left are disjunction and negation. Disjunction, thankfully, has probably the easiest introduction rule. Disjunction is if you have a sentence, you can bolt on or whatever. Right? And the idea here is that, look, if you know that A is true, then A disjunction, whatever sentence you like, is also guaranteed to be true. Again, that's a rough way to get a grip on it, right? So if you have a sentence, you can stick on or whatever, any whatever, right? B can be any sentence you like. Disjunction introduction is easy because disjunctions are cheap. They're easy to make true. Disjunction elimination is hard because disjunctions are cheap and they're easy to make true. So the problem with disjunction elimination is, we can put it this way. It's hard to know what is true in light of a disjunction. Because think about it. Suppose you have A disjunction B. There's 3 different ways that could be the case. It could be that A is true and B is false. It could be that B is true and A is false. Or it could be that both of them are true. And when we're assessing things just purely at the syntactic level, which is what we're doing when we do natural deduction, we don't know which one of these 3 it is. So we have to come up with a rule that gets around that problem. And here's the idea. Right? Suppose that we can show from one of the disjuncts you can get to some result, and also from the other disjunct that you can get to the exact same result. Then it wouldn't matter how it is that the disjunction's true, because all routes lead you to that result. So here's a jokey example, right? You can get to the C via going through Rotterdam. You can get to the C via going through Antwerp, right? But it doesn't matter which way you go, you end up in the sea. So if I know that you've ended up in the sea, I don't care which route you took, you ended up there. The general thought is we won't necessarily know why the disjunction's true, but we won't care, because we will have shown that no matter what happens, it gets you to the same place. So, how does disjunction elimination work? Okay, I'll give you the rule. It is hideous. We need a disjunction, and then we're going to need 2 subproofs. One subproof that starts with the left disjunct and gets us to a result. Another subproof that starts with the other disjunct, the right disjunct, and gets us to the exact same result. We can then conclude that the result follows from the disjunction. Why? Because we know no matter which way you take, you end up in the same place. So it doesn't matter if the disjunction is true because A entails C. It doesn't matter if the disjunction is true because B entails C. If they're both true, cool, you're really getting to C. Right? So what we need is, again, a disjunction that we eliminate 2 subproofs from either disjunct that take us to the same place, and then we get that result. And our citation here is lengthy. We need to cite the disjunction that we're eliminating, that we're using, and the 2 subproofs to show you that from this disjunct you get to here, from that disjunct you also get to here. This is by far the most complicated citation. Right? It's also one that tends to throw people off. The thing to remember when you're doing disjunction elimination is that you need both subproofs, and they have to end up in the exact same sentence. Because what you're showing is that no matter which way you take, you end up in the exact same place. Yeah.
The only thing that's throwing me off is that I can't see C anywhere above.
Good. So that's the nice thing, right? Because we kind of don't really care how it is you get to C, right? C is just some output sentence. C, in fact, could be A in both cases. We'll talk about one where that is the case. One of the examples that we'll go through in a few slides does exactly that. Remember, these are all in my sexy squash font, so they could be any sentence we need. C in this case is just our result sentence. It is our destination. Okay, so now we've got 4 out of the 5 connectives. The only one left is negation. The problem is negation is very strange. Negation, by its nature, seems to involve truth because it's a truth value flipper. So we're going to have to introduce another tool to help us make sense of negation. And to do that, we're going to introduce my upside down T. My upside down T is a very special symbol in this system. It is our contradiction symbol. So if you see upside down T, it is a shorthand way to say problem. You've got a contradiction. So here's the rule for negation introduction. Negation introduction says if you have a subproof that starts with a sentence and ends in a contradiction, then one line to the left, you can negate the sentence you started with. What's the idea? The idea is if A is true, a contradiction follows. So A must be false. That's what this reasoning shows. Assume A is true, you get a contradiction. So A must not be the case. So we cite our subproof, and the result we get is the negation of the opening assumption of that subproof. Again, if this were true, bad stuff happens, so it better not be true. That's negation introduction. Negation elimination is if you have a sentence and its negation, you derive a contradiction. Interestingly, this is also called contradiction introduction because that is the only thing it does. You have a sentence and its negation, you have generated an upside down T. You have set us up the bomb. So one thing that's very strange, to go back a line or to back a slide, every time you do a negation introduction rule, what rule will you have to use inside the subproof? You will always use negation elimination inside a negation introduction subproof. That sounds really strange, but the only way to get the upside down T is via this rule. So every time you do negation introduction and you have your little subproof, in the subproof you will have had to have done negation elimination. In other words, you will never get negations from nothing. Now this upside down T also gives us something really funny, and my favorite rule. My favorite rule uses the upside down T. My favorite rule is explosion. The idea here is if you're dumb enough to believe a contradiction, you're dumb enough to believe anything. That is, from the upside down T, we can blow it up and get any sentence we want at all. Now the rationale here is something we've talked about all the way from lecture 1. Remember Mars's moons. This is the same problem. If you have a contradiction, something that can never be true, then anything you like will follow from it. That's what explosion encodes. You take your bomb, you blow it up, and you get any sentence you like. But note, the sentence has to be on the same line as your bomb. It doesn't let you derive anything a line to the left. So explosion is very powerful, but it's a restricted explosion. It's a focused explosion. Okay. And finally, we have the wankiest named rule. This is us as logicians deciding we want to be posh, and we use Latin. The last rule is tertium non datur, or in plebeian talk, no third way. And the nice thing about no third way is that it effectively is a version of disjunction elimination. Because what it's eliminating is the disjunction that for every sentence A, either A or not A. So we know that for every sentence, it's either true or it's false. So what tertium non datur says is, hey, assume a sentence is true. If you do that, and you can get to some results, but you can also assume the sentence is false and get to the exact same result, then it doesn't matter, that result must be true. Two subproofs, one that starts with a sentence and ends in some result, another subproof that starts in the negation of that sentence, ends in the exact same result, conclusion, result must follow. Because that sentence is either true, which gets to your result, or it's false, which gets to the same result. And note our citations here. And this is one of the things that kind of gestures at how it is disjunction elimination. The only thing missing here is the cited disjunction. That's because it's basically kind of given. We know that for every sentence, true or false. Okay. These are all the rules! Yay! We're now perfectly conversant. We can start playing the game. Right? You can now construct any natural deduction proofs that are possible for truth functional logic. Or put more generally, we can now construct how it is idealized reasoners would go from premises to conclusions. And we can generate maps that will actually provide insight. We know why it is that certain premises guarantee certain conclusions. And we can give these proofs that give you mappings, that show you how to walk, what steps to take from premises to result. Okay. Now, before we talk about anything else, pause, ask, what questions do you have for me so far? Yes, please.
In negation elimination, we don't have that subproofs because we are adding negation A, so like we don't need.
So there's no subproof with negation elimination. Importantly, you already need to have a sentence and its negation, and you stay on that same line, whether it's your main proof line or in a subproof, and you generate your contradiction.
Because we are adding something.
Again, this is why when we think about negation elimination, you can also call it contradiction introduction, because that's all it does. It keeps you on the line you're on, and it gives you your upside down T. Yes? So, not necessarily. It will depend on the kinds of things that we'll need to do. The nice thing is that a lot of times we'll be able to just stay on proof lines or subproof lines. But as we go along, we will have to eventually get 3 layers deep. I think there's 1 or 2 questions in the homework that are a little bit more complicated than that. The nice thing is it's almost always going to be very transparent as why we're doing subproofs. Right? Because one of the parts we need is a conditional, say, something like this. So the things to remember here. First, you're going to get the rule sheet, right? I'm going to give you the cheat sheet as part of your exam. It will include all of this sort of stuff, right? It will give you the descriptions of how the rules work. But of course, if you don't know how to read the rules, then it's going to be pointless. The other thing to note is you don't have to memorize them. Again, get the sheet. But the more you're kind of internalizing these, the easier this stuff's going to be. Okay. So, I want to wrap up by talking to you about some tools that you can have or use that will save you some time. Note that every rule we're going to talk about from now on is just simply a time saver. It's an indication that I could have done this with the other rules, but I'm just saving myself some lines. Okay? The first one's going to seem absolutely ridiculous, but it's useful. The first derived rule is reiteration. Reiteration is you can literally repeat a line. So if you have a sentence anywhere in your proof, you can repeat it. Seems silly, it's actually useful occasionally. So, reiteration, you just cite the line you're repeating, and then you repeat the sentence. Now, for the next one, the next derived rule, it's helpful for us to go through. Yeah.
So, for example, we need to put in A, we can use A, repeat A, and then write 1, 2,
and bingo, right? So you could reiterate A, and then do conjunctional elimination on 1 and 2, and you get A conjunction A. There you go. Yes?
Can we reiterate subgroups?
Nice. So no. Reiteration only lets you repeat individual lines. And importantly, if one of the lines that you're trying to reiterate appears in a subproof you've closed, because that rule always trumps. Whatever's going on inside a subproof, if we've moved out of it, all of those lines are gone. We can never use those lines anymore. So that does mean that sometimes there'll be sentences that you want for multiple subproofs. So you're either going to have to get it twice, or you can get it in the main line and then use it multiple times. Okay. So reiteration is just repeating yourself. For our next derived rule, it's helpful to talk through an example. So for this example, we're going to have two premises. We've got A disjunction B, and we've got negation B. And we want to show that A. So before we dive into it, let's just think about it, right? Is this argument going to be valid? What do you think? Valid? Invalid? It's valid, right? So again, you can see it. We've got A or B. We know it's not B, so it must be A. Okay? All right, so let's formalize the reasoning. So we start our proof. We start our proof the same way we always do. We list our assumptions vertically. We draw our assumption line underneath them. We drop our proof line. Now, how are we going to use our rules to get to A? Well, what do we have to play with at line 3? We only have sentences 1 and 2. And unfortunately, these two don't really give us a whole lot to work with. 2 has a negation as its main operator. And negation elimination, we need to have the unnegated sentence to do anything. So it looks like it's going to have to be using 1. So if we're going to use 1, what rule are we going to use? What rule could apply to sentence 1? Disjunction elimination. That's its main operator. So we'll run disjunction elimination on line 1. Now, how does disjunction elimination work? Remember, we talked about it about 15 minutes ago. It requires two subproofs, one that starts with one disjunct and gets us to a result, and one that starts with the other disjunct and gets us to the same result. So let's think. What result could our two subproofs try to get to? They can get us to A. They can both get us to A. Right? One of them's really easy. We assume A and we use reiteration. The other one's a little more complicated. If we assume B, how are we going to get to A? Let's think. If we assume B, do we know anything about B from our initial assumptions? We know it's false. Cool. So we would then have B and its negation, which sets us up to use negation elimination, right? To get a contradiction, and then we use explosion. So here we go. Let's talk through it. Don't worry. It's easier to see, right? Remember the big structure. The big structure is going to be using disjunction elimination. So we're going to want two subproofs. Let's start with the one that begins with B. Okay? We want this one to result in sentence A. So what do we have accessible right now at line 4? We can use everything that's on this subproof line, which is only line 3. And we can use everything on the line to the left. So we can use sentences 1, 2, and 3. If we take sentences 2 and 3, we can apply negation elimination to give us our contradiction. Yeah? With me so far? Okay. Now that I've got a contradiction, we get to use my favorite rule, because from a contradiction, anything you want follows. We can blow up the contradiction to get any sentence. Now I want this sentence A. Why do I want A? Because remember the big plan. The big plan is to give two subproofs that both end in the same place. And we're going to want them to end in A. So, my subproof has got me, one of my two subproofs has got me to A. What's next? What do I want to do at line 6? We're done with this subproof. Cool. So we can step back into our main proof line. But then what do I want to do at line 6? What sentence do I want to get? Yeah, we're going to open our second subproof. And what does this second subproof start with? A. It's our other disjunct, right? Because remember, the big plan, disjunction elimination, two subproofs. We're Bon Jovi. We're halfway there. We got to do the other half. So we start with A. And we want this subproof to end in sentence A. So what rule will we use? Yeah, reiteration. Hey, it's actually showing its worth already. So now look at what we've got. We've got a subproof that starts with B and gets us to sentence A. We've got a subproof that starts with A and gets us to sentence A. So what can we derive at line 8? We get sentence A, and what's the rule? We're going to mention both the subproofs. What's the rule that we use, though? Remember, disjunction elimination. So we cite the disjunction we've used. We've eliminated the disjunction in line 1. We cite the two subproofs to show us, hey, from this disjunct you get to this result, from that disjunct you get to the same result. Boom. That's why we know the result follows. No. So importantly, once we've moved out of the subproof, once we've discharged it, like we did, say, at the end of line 5, every individual sentence in the subproof is inaccessible now. So we can't use lines 3, 4, and 5 anymore. We can cite the whole subproof to do something, but the individual lines are gone. Cool. Yes?
Why couldn't we start from the second step? Why couldn't we start from the second step?
Ah, you mean that one around? Here's the nice thing. We could have done it either way around. It doesn't matter about the order that these subproofs are in, just that we have both subproofs.
No, I mean, why couldn't we eliminate negation?
Good. So importantly, to eliminate negation, we need to have a sentence and its negated form. And when we started, all we had was the disjunction at line 1 and negation B. We did not have unnegated B. We needed to have that as an additional assumption. But of course, where were we going to get it? In this case, we got it from our disjunction in line 1. Okay, so all of this, yeah.
In 3 to 5 subproof, they're saying that we don't have, it cannot be B, so it must be something like, right?
So what the subproof shows is that if B were true, we could get to A. And the way that we get there is via this explosion. Right? It effectively shows, look, if B were true, bad stuff. And from bad stuff, anything follows, including A. So from B, we can get to A. Okay, now all of this is to get us to a derived rule. Because whenever you have this sort of structure, you can do this chain of reasoning. Right? If you have a disjunction and the negation of one of the disjuncts, you can derive the other disjunct. Thus, our next derived rule, disjunctive syllogism. It says just what I said. If you have a disjunction and the negation of one of the disjuncts, you can derive the other one. Because again, if you know A or B, and you know it's not B, then it must be A. Or the other way around, A or B, you know it's not A, it must then be B. Disjunctive syllogism just saves you a bunch of steps. And you cite the disjunction and the negated disjunct. Cool? So there's just a couple more derived rules. The next one, modus tollens, is effectively the inversion of conditional elimination. It tells us if you have a conditional and you know the consequent is false, then you know the antecedent is false. Put another way, if you have a conditional and you have the negation of the consequent, then you can derive the negation of the antecedent. Note, it only goes that way. It only goes against the arrow. Because the negation of the antecedent does not guarantee the truth or falsity of the consequent. So conditional elimination says if you've got conditional and you know antecedent's true, you get consequent. Modus tollens says if you've got a conditional and you know the consequent's false, then you know the antecedent's false. Those are the only ones we can get from conditionals. The next to last derived rule, a very simple one, double negation elimination. If you have not, you can erase them. It's a simple rule. It's actually nice to keep it separate because we'll talk about it being potentially distinct. And the last derived rule is actually a quartet. It tells you that certain sentence structures can be swapped with other ones. These De Morgan rules will actually be very, very, very familiar. So take our first one. If you have negated disjunction, you can turn it into a disjunction of two negations. If you know not both are true, then you know at least one is false. And vice versa. right? The De Morgan rule lets you go backwards and forwards, whichever way you want. So that's one pair that the De Morgan rule lets you do. Can anybody guess what the other one is? It's going to be neither nor. The two ways we can do neither nor. So if you have a negated disjunction, you can turn it into a conjunction of two negations, or vice versa. Now, the reason to mention these is they're very handy, right? It's really difficult to find much you can do with a negated disjunction, but it's very easy to make use of conjunction of two negations, for example. So again, what these rules do is let you play around with syntactic structures. Okay. So how are we feeling so far? Everybody okay? Again, to stress, I'm throwing an absolute ton of rules at you. And I understand that. Don't panic, because we're going to keep talking about them for the rest of this week in the tutorials. We're going to talk about them again next week. In fact, it's worth mentioning, right, something about next week's lecture. Right? So next week's lecture will not be in person. I'm going to be away. I've got another thing I have to do, unfortunately. So next week's lecture will be a recording. I'm going to put that up by Thursday. Similarly, unfortunately, that also means next week's tutorials will not be happening. But what I will do is I'm going to make a recording going through, just me with my little whiteboard, going through all of the problem sets for the homework for next week. Right? That is, not the ones that's due next lecture, but the ones we would do in the tutorials next week, to give you an instance of how all of these go. But importantly, right, again, don't stress. Right? We're going to talk next time about how to use these systems to track syntactic properties, parallels to all the semantic notions. Well, have a go at some of these, take care, and we'll see you all in the tutorials.